Good afternoon, everyone. Thank you for joining us today and letting Framatome bring ingenuity and creativity to some of the complex challenges we face at a nuclear power plant. My name is Umar Faraz. I'm the Vice President of Regional Accounts at Framatome, and we'll be your host this afternoon. As an industry, we're always committed to continuous improvement. The nuclear sector focuses on making our nuclear plants run more effectively, efficiently, and cost effectively. This can be accomplished only by innovative thinking and innovative practices. Today, we will talk about some of those solutions that started at a power plant in collaboration with our customer to solve some of the complex problems, which ultimately ended up saving utilities critical time and operating cost. As Framatome, we begin every meeting with a safety message. So today, our safety message is about lifting and rigging operations. For a lifting and rigging operation has to be planned. It has to follow a lift plan or procedure. Obviously, it's supervised and it's done with the highest rigor so that maximum safety margins can be achieved. If you are conducting a lifting operations, you'll always see a red barricade tapes go up. You should not be under the load or in the load path. And if you're not supposed to be, or if you can be away from the lift area, I highly recommend you do so. With that, I'll go in with the introduction for our guest speakers today. Our first speaker is Stephen Redmond. Stephen Redmond is an outage services engineering supervisor located in Lynchburg, Virginia. He has been with Framatome for the last 9 years. He graduated from Virginia Military Institute with a bachelor's degree in mechanical engineering. Stephen will be discussing how Framatome newly designed spent fuel handling tool implemented at TVA Watts Power Plant. Followed by him, our speaker will be Nate Andrew. He's a component and structural analyst located in Lynchburg, Virginia as well. He's been with the company for the last 2 years and graduated from University of Virginia with a Bachelor of Sciences in Mechanical Engineering degree. Nate will be discussing Framatome Statistical Baffleboard Analysis Program. Our last speaker will be Josh Templeton, a mechanical engineer located in Richland, Washington. He has been with Framatome for the last 10 years and graduated from Washington State University with a bachelor's degree in mechanical engineering. Josh will be discussing Framatome's additive manufacturing channel fasteners, which were recently installed at Browns Ferry unit. With that, I'll turn it over to our first guest speaker today, Stephen Redmond.
Thank you. Good afternoon. I'm Stephen Redmond. Like Umar said, I'm a supervisor in Framatome's outage service engineering group. And the main focus of our group is to help develop tools to support PWR and BWR refueling outages. One of the tools that we developed over the past year is our new spent fuel handling tool for Watts Bar. The need for this tool was driven by issues with the elevation stack up in the Watts Bar spent fuel pool. Similar elevation issues exist at other sites throughout the industry. The challenge with the elevation stack up at these various sites is that the controls to latch and unlatch the OEM spent fuel handling tool are located well below the spent fuel bridge handrails. At Watts Bar, this causes the operators to have to get down on their hands and knees and reach through the handrails to actuate the tool, similar to the picture on the right. During the course of a standard refueling outage, these operators have to do this over 772 times. This makes the task of moving spent fuel more difficult and adds extra strain to the operators. To solve this problem, we leveraged our experience building other long handle tools, such as our CRDS latching and unlatching tool, our RCCA tool, and other spent fuel handling tools to develop a new motor-driven spent fuel handling tool. This new motor-driven tool is powered by a single commercial off-the-shelf battery and has handlebars and a control pendant that raise the controls to an elevation that does not require the operators to get down on their hands and knees to actuate. As part of the development for this tool, we collaborated with TVA to ensure the design would meet all of their needs. We also worked with them to conduct an extensive elevation study to optimize the tool length and ensure that the controls would be easily accessible to the operators. By working closely with TVA and utilizing components from similar long-handle tools that we've built in the past, we were able to create a simpler, more robust, and more reliable spent fuel handling tool. The simplification to this tool is the ease with which it can be operated. The tool is able to be operated from a standing position, and it eliminates the fatigue associated with getting up and down on your hands and knees and any errors that may occur because of that. The ease to operate also reduces the time required to latch and unlatch fuel assemblies. And over the course of an outage or a dry cast campaign, this can add up to reduced times in the actual fuel movement activities. The increased robustness and reliability is centered around the gripper that is used for this tool. It is the same gripper that is located on the mast on the manipulator crane inside containment. Incorporating this gripper onto this tool allows for added safety in that a mechanical interlock is now present on the tool that prevents the tool from being able to be actuated when the tool or the fuel assembly that it is carrying is not fully seated down in the rack or in the upender. Framatome has already fabricated and tested the first spent fuel handling tool in our technical training center here in Lynchburg, Virginia. This tool has been delivered to Watts Bar, and we are currently in the final stages of testing the tool and conducting training with Watts Bar's operators. The next step is to build a second tool for Watts Bar, which will be delivered by the end of September. The same testing and training will be conducted again at that time. By the end of the year, we will be building an additional 2 tools that will be sent to Sequoia. Same testing and training will be conducted with their operators. We still need to perform an elevation study with Sequoia to ensure that the tool will work there, and there are not any changes that need to be made to the current length of the tool to have it fit appropriately at Sequoia. This elevation study will be conducted over the next few weeks with TVA. Overall, this was a pretty fun and interesting and challenging project to work on, but it's not the only type of long handle tool that we work on. We have a lot of offerings when it comes to long handle tools, both in spent fuel and in containment, and we're always willing to work with customers to see what challenges they may have and how we may be able to solve those challenges with the various tools that we offer. Thank you all for your time. With that, I will turn it over to Nate Andrew.
Thank you, Stephen. Good afternoon, everyone. My name is Nate Andrew. I'm going to talk today about our aging management tool, Rosetta, which addresses baffle-deformer bolt degradation. As some background, let's take a look at what baffle-deformer bolts are and discuss what challenges are posed by their degradation. The right picture on this slide shows a cutaway of a typical PWR lower internals assembly. The core barrel forms the outside, and inside you have vertical baffle plates and horizontal former plates. These plates are held together with baffle deformer bolts, and you'll also hear me refer to them simply as baffle bolts. This assembly guides the reactor coolant flow through the fuel. Each baffle plate requires a certain configuration of bolts to maintain the design functions. And with some variation among reactor types, there are roughly 30 baffle plates and around 1,000 total baffle bolts spread out across them. Of these bolts, a high number of them are redundant, and as such, there are countless combinations of bolt patterns that can be shown to be acceptable. Unfortunately, these bolts are subject to IASCC, or irradiation-assisted stress corrosion cracking. This has been observed as early as the 1980s, and every PWR in the US has a routine inspection plan for these bolts. Recently, however, several units have experienced unexpected levels of degradation. While generally shown to not be a nuclear safety issue, identification of such degradation can quickly lead to unplanned outage activities, and these activities have added weeks to outage schedules in the past. Now, obviously, this is something we want to avoid, but bolt degradation varies significantly from plant to plant, and so how do we account for that? It's also expensive to prepare and deploy a bolt replacement crew as a contingency plan. So this leads to another question. What's the right level of contingency planning investment? These are the challenges that motivated the development of our statistical analysis tool. Framatome has a proven patented solution, and it's an NQA1 level software package called Rosetta. This package incorporates all the major tools in the baffle bolt aging management toolbox shown above. This includes a key Framatome innovation, our advanced predictive model that projects future bolt degradation. The program's analysis begins with the inspection results, then considers missed inspection calls and future degradation, and finally evaluates millions of configurations against the design basis in an hour, providing the probability of meeting the design basis as a function of operating time. This evaluation happens as fast as inspection results are obtained. With this, we work with each plant to determine the optimum combination of examination coverage, re-examination interval, or plant modifications to meet their aging management objectives. We've developed this program with the support of the PWR Owners Group. Over 50% of Westinghouse and B&W units have bought into this program. So what are the benefits of using the Rosetta baffle bolt analysis tool? First of all, Rosetta's predictive capability allows plants to estimate the risk of not being able to meet their design basis ahead of an outage. This will reduce contingency planning costs by optimizing the scope of the replacement plan. Secondly, the program will reduce risk to the outage schedule by providing results fast enough to give actionable intelligence as quickly as UT results can be obtained. Third, and perhaps most importantly, the program is flexible enough to respond to whatever is thrown at you during an outage, be it an issue with bolt inspections or even bolt replacements. Rosetta can handle it. This keeps you on your critical path by avoiding extra activities that don't contribute to maintaining the design basis. In summary, Rosetta provides a risk-informed basis for choosing the right aging management options for baffle bolt degradation. This will keep you on budget and on schedule. So let's talk about two recent examples of how Framatome worked together with utilities to make their baffle bolt examinations go as smoothly as possible. In fall of 2020, Framatome worked with Duke Energy prior to the Oconee Unit 1 outage to estimate the likelihood of being able to justify continued operation without an acceptable bolting pattern analysis, and we developed a plan in accordance with their risk tolerance. Thanks to Rosetta's flexibility, we were also able to respond emergently to unanticipated inspection results. We avoided impacting the outage schedule, and we were able to justify another cycle of continued operation. In recognition of our work together, Framatome and Duke Energy were given a TIP award, as you can see on the left, for advancements in reactor internals, baffle bolt inspection tooling, and engineering analysis techniques. And this was in part due to the innovative in-outage use of Rosetta. Also, just this spring, Framatome worked with Dominion for their Surrey Unit 1 outage. Prior to the outage, we evaluated hypothetical scenarios that challenge Rosetta assumptions to better prepare for unanticipated results. During the outage, we were able to provide consistent, rapid turnaround of interim results. And while we were prepared for the worst, everything went very smoothly. And at the end of the day, we showed that no bolt replacements were needed to operate for 10 years. We're currently preparing to implement Rosetta at other plants both this year and the next. We're also working with the owners group to update Rosetta to include recent operating experience. As we receive more inspection data, we can improve Rosetta's predictive capability. And lastly, we're working to extend the statistical analysis to cover the impact of flexible operations. Rosetta is just one of many examples of Framatome identifying the customer's need and creating the optimal solution to address that need. But Framatome's commitment to our customers extends beyond developing new solutions. As you can see, Framatome is also focused on maintaining and improving our products to ensure we will continue to provide quality service. I'd like to thank you all for listening today, and it's my pleasure to introduce our next speaker, Josh Templeton.
Thank you, Nate. I'm Josh Templeton. As an engineer in Framatome's BWR fuel design team, I'm happy to share some information today about the additive manufactured channel fastener project recently completed for TBA. I'd like to preface this presentation by saying that additive manufacturing, or AM for short, has the power to revolutionize manufacturing in the nuclear industry. Among its advantages is allowing for accelerated time to market. For the nuclear industry, where each step in the process of development, design, testing, analysis, and qualification can take a long time, additive manufacturing can potentially be a game changer. So the challenge presented to Framatome was to go through each step in that process for a component using a manufacturing technology with limited to no previous in-core operating experience. Is to fabricate and qualify a safety-related additive manufactured fuel component and then operate it in a TBA reactor. And safety-related is easy enough to say, but a safety-related component is a component designed to mitigate the consequences of accidents that could cause undue risk to public health and safety. So that really elevated the threshold of design and quality required to ensure that this component would be qualified and would perform its intended safety function. And this challenge was collectively taken on by Framatome, Oak Ridge National Lab, or ORNL, and TBA. Each partner had their particular role, with Framatome focused on the design and quality inspections, ORNL focused on fabrication and characterization, and TBA accepted it and operated the component in their reactor. And the solution to this challenge became the additive manufactured channel fastener, which you can see in the picture on the left. This channel fastener is a component that mounts to the outside of the fuel channel and functions to keep the 4 fuel assemblies in each individual core cell separated to ensure the reactor can meet control blade insertion requirements. This component was chosen due to its relative simplicity in both design and function, which maximized the project chances of success and minimized project risk. The solution included a first-of-a-kind product technical file of drawings and specifications, which are uniquely tailored to additive manufacturing. The Framatome design team started work on the drawing by considering each feature on the component for its printability. We also sought ways to minimize or consolidate post-processing, because when component handling is minimized, processing efficiency and product quality are increased. Framatome then innovated and adapted the design in an effort to balance functionality with manufacturing. With respect to the product specification, Framatome had to consider the design requirements for powder and flowability, as well as other unique inspection methods, such as computerized tomography. And of course, everything had to meet the quality requirements of a 10 CFR 50 Appendix B program. This required additional effort by Framatome quality teams to independently verify all critical product characteristics in order to ensure product compliance. And so the benefits of this project, or one of the greatest benefits, is that now there's a safety-related additive manufactured component operating in core. And this is a critical beginning step towards furthering the use of additive manufacturing in the nuke industry. Through pilot campaigns in the future, these components, by comparison with our digital twin, will allow further characterization of additive manufacturing performance in an irradiation environment. In addition, Framatome now has that technical knowledge and experience of going through this full process from development to delivery, which will help inform future projects, acting as a stepping stone to bringing future additive manufacturing components to our customers. And these future additive manufacturing components could be parts for fuel interface tooling, like the spent fuel handling tool that Stephen Redmond discussed earlier, or replacement parts needed quickly for critical path work, or they could be completely unique components for one-time custom applications. The result is that this project has placed Framatome in a unique position and give us another highly versatile tool in Framatome's toolbox to support our customers' needs. As mentioned previously, this really was a unique and collaborative effort alongside Oak Ridge National Lab and TBA. Each entity brought their unique skills to the table. The Framatome and ORNL teams work closely together with recurring status meetings to provide a format for clear and regular communication of project milestones and schedule. Smaller focus groups met regularly as Framatome helped ORNL to understand the function behind the features on the component, and also as ORNL helped Framatome understand how to adapt those features for additive manufacturing. ORNL was tasked with successfully fabricating 16 fastener components, as well as all required test specimens in just one single build run. They and I understand just how much effort it took to develop the final build structure and layout, which is shown in the top right photo, as well as the post-processing and characterization. They are an amazing group of people with amazing capabilities. And TVA was also critical in providing the capability, willingness, and support to operate these components in their Brownsville Unit 2 reactor. When utilities and fuel suppliers work together for a common goal, it really broadens the scope of what can be achieved. And finally, I want to add that much of this project took place during the height of the COVID pandemic. The close cooperation between all these teams was key to this project's success. And I want to acknowledge and thank the teams at ORNL and TVA for their critical work to make this project successful. So what are the next steps? We can't just say that we did it and call it a day. Instead, Framatome is working to extend our collaborations with other additive manufacturing suppliers, as well as other utilities, to further introduce additive manufacturing into the nuclear industry. Framatome already has projects underway to take additive manufacturing to more complex geometries, targeting unconventional designs. And beyond fabricating additive manufactured fuel components, Framatome has leveraged AM to reduce manufacturing support costs while increasing quality. Additive manufacturing parts now support fuel manufacturing and fuel shipments. We've also utilized additive manufacturing to reduce Framatome's R&D project cycle time to bring our customers faster solutions in less time. In summary, Framatome's ability to innovate and the possibilities of additive manufacturing technology really are limitless. Thank you for your time, and I'll turn it back over to Umar Faraz.
Hey, thanks, Josh. Thanks for sharing your thoughts. Stephen, Nate, thanks for bringing your knowledge and experience and sharing it with our customers and colleagues in the industry. As you can see, innovation is at the center of Framatome and its people. It is our goal to have continuous improvement mindset for the long-term safety, reliability, and customer affordability. Framatome is continuously working on solutions like the one presented today to solve some of the complex problems we see in day-to-day at our nuclear power plants, which can lead to cost efficiencies. I hope everybody found this webinar to be helpful, and some of the information we presented today can help you solve some of the complex problems you see at the nuclear power plants. With that, let's just unmute everybody for have some Q&A for our presenters.
I had a question on the channel fastener. Is just the base portion additive manufactured, or are you looking at also springs and bolts? So what are the limitations of additive manufacturing as far as, the ability to retain, like for bolts and such, or is it just for structure? Thanks.
Yeah, so the feature that was actually printed was the main body of the channel fastener. The bolt and the spring attached to it were not printed. The purpose behind that was really to simplify the project as an initial first step to get additive manufacturing operating in the reactor. Certainly there are limitations when it comes to material thicknesses and performance requirements that will impact additive manufacturing components, their performance in core. But for this particular project, we limited to just the channel fastener body. For future projects, it's being expanded to include parts of various geometries, various thicknesses, features that are much thinner than what the channel fastener are. So we are working in incremental steps to address and look into those items and taking it kind of one step at a time. But I wouldn't say that there's any particular limitation at this point in time. It's mainly working through the process step by step and finding a solution to it.
All right, thanks for clarifying that answer over there, Josh. I did have one question come through, actually one more now. One is for Stephen here. Stephen, you mentioned this particular tool was specifically utilized at Watts Bar. What is its availability, or how does the design change for its implementation at other PWRs?
So the tool was built specifically around, or it was designed, like you said, initially for Watts Bar, but the tool is applicable really to any other Westinghouse PWR spent fuel. There are some things that we would need to take a look at, whichever site we're providing it to ensure that it's designed to fit that site. So if you look in containment, most everything's pretty uniform over there. When you get to spent fuel between different sites, there's a lot of variations between the sites in hook height, in depth where the racks are located, different obstructions that you might have. So we can adapt the tool. We would just need to get information about the specific spent fuel pool that we're going to deploy the tool into so that we can design it around that tool. The overall function and design of the tool doesn't change. So your gripper will still remain the same. Your controls up top will remain the same, but the lengths of the tool and where the controls land might vary between the sites.
So you just have to work with the dimensional inputs with each site, and you can make the tool flexible for their needs.
Correct.
All right. That's good. Nate, I got one for you here. You mentioned about evaluating the hypothetical results that challenge certain Rosetta assumptions. What does that entail?
That's a good question. Thank you. So as Rosetta results, they rely on a predictive degradation model. So when we're analyzing inspection results, it's important to recognize and account for any incongruencies between the results and operating experience, because there are certain assumptions built into Rosetta that are based on current operating experience. So if we see bolt degradation that falls outside of that, it needs to be taken into consideration. Those kind of results are characterized by either an excessive overall number of bolt failures, asymmetrical degradation, and unexpectedly high local degradation. So how we handle those unanticipated results is a case-by-case basis. It depends on the type of unexpected results we're seeing and how severe it is, how outside the norm it is. That's what I had in mind when I was talking about unexpected results.
Thanks, Nate. I got another one coming to the chat box. It's for Josh. Josh, what is the knowledge transfer you guys gained from the channel fasteners which can be applied somewhere else within the fuel components or others? Was there any good OpEx learnings?
We spend this time focusing on one particular component, but in reality, additive manufacturing is really independent of any particular component feature. And so it really is a very versatile tool that can be applied to any fuel component or definitely other fuel components, as well as other tooling or any kind of equipment that, replacement parts that may be needed. And so the entire process of going from sort of a somewhat established design to adapting that design to make it printable, all the knowledge that we gained really transfers to any component you may end up printing, regardless of its size, of its features, or that. And so a lot of this experience is going to be directly informing what we do in future projects to make components that are much larger than what the channel fastener was, as well as components that have very different shapes and features. The real key of additive manufacturing is to focus on those parts that are unmanufacturable with standard technology, something that's unmachinable, that can only be fabricated when you 3D print it. This really opens up, especially in BWR reactors and in PWRs, this really opens up debris filters at the bottom, the lower tie plate of the fuel assembly, to really limitless designs that can enhance debris capturability. And so the entire process is completely transferable to any other project we may work on with additive manufacturing.
Thanks for addressing that, Josh. I think it's really interesting because additive manufacturing has taken a run for itself, not only within the nuclear industry, but others as well. So I think it's going to be a growing market, not only within the fuel side of the house, but also for the components and within the reactor services side as well. Okay. I just want to thank everybody for joining in today on the webinar. I want to thank our speakers today. I think if you guys can think of any other questions later for our guest speakers, I have their contact information up on screen. You can reach them out to them individually to ask any specific details or further questions if you want to go into the more technical details on any of the solutions presented today. You can always go to Framatome Solutions portfolio to look at other solutions where we have developed and out there in the industry implemented at our power plants. I encourage you to guys connect through our social media campaign as well. I want to thank everybody for joining the webinar. I want to thank our customers and their time. I want to thank our presenters bringing some of the solutions to some of the tough challenges we see on the plants on a day-to-day basis. I wish everybody rest of the day safely and joyfully. I appreciate everybody joining. With that, end the webinar.